And we are recording. Hey, couple administrative announcements. We're up to 22. Look at that, 27 people missing, just like that, 23. First thing, if you've looked at the schedule, which is in the syllabus, you'll notice that we're about a quarter of the way through the semester with the conclusion of this week. And at the fifth week, that's about a third of the way through the semester. And that's when we do the first midterm. And so it's currently scheduled for next Friday, and I think I'm going to meet that date. And, people always ask me, okay, how do I prepare for your exam? Okay, and it's a good question. And you may notice, in fact, some people will go, can you give us like a practice exam? I had one student in one class here at Washington College say, can you give us a study guide? And we had a name for that at the Naval Academy. We called it the gouge. It's the shortest distance between 2 points, the way to get to what are you going to ask me on the test? And, while I don't guarantee these are questions that are going to show up on the test, I want to remind you of something I've been publishing, and there'll be one more of these before the exam next week. Let me share my Canvas screen with you. That looks like Canvas right there. Good. I should change glasses to the ones that allow me to see computer screens. If you're looking at my Canvas screen, you're seeing under assignments, the homework. And the first 3 sets there are extra practice for chapters 1, 2, and 3. And later on today, there'll be another one. You'll have homework for chapter 4, which is what we'll be finishing up on Friday. And then there'll be an extra problem set for chapter 4 as well. And so my best advice is to review your worksheets, be able to do all those problems, review your homework if you choose. If you want to do some new problems, there'll be 4 extra problem sets available for you. And, that's what you're going to do. I would just tell you, physics is a doing subject. You're going to solve problems. Yeah, you have to know some knowledge. There are some conceptual ideas you have to get, but the overwhelming majority of the questions on the test will be problems and doing the things that we've been doing during class and that you've been doing on your worksheets and things like that. All right, so that's the first announcement. Questions on that?
I have a question about
Sure,
the
go ahead.
midterm. Is it gonna be like we have to type out all the equations on the computer, or can we like do it on a piece of paper,
Yeah,
the
no,
exam, and then submit it?
I haven't finalized the format. And if you notice, you've been doing mastering problems, and all I see there is your right answer, right? And you've also been doing worksheet problems where I look at your work and I see your process, your method. And what I've got in my mind is probably about 75% of the exam will be in mastering. And I suspect I'm going to pick a lot of multiple choice type questions. There'll be problem solving, but one of the answers will appear as one of the 4 or 5 choices to the multiple choice problem. But I'm also going to include a section that's like a worksheet with 1 or 2 problems that you do out by hand, and you upload those into Canvas. So I think the answer to your question is a mix, is what I'm currently planning.
Okay, sounds good.
Yeah. Okay. And the other thing is, resources available. Okay. As we've been going online starting last semester, it's really kind of hard to expect the same kind of exam security that you would if you were sitting in a classroom in Dunning Hall. And so what we've done in the past is I've gone with open book. Um, you can go look at any resource you want, other than somebody else doing the problem for you in any manner that could happen. Okay. I'll also provide, so you don't have to keep hunting through your electronic textbook. I do have an equation sheet made up, and so that might be all most people would need. Basically the place you would go to find equations, because you're not required to memorize them in this course, is the back of each chapter. There's a little summary section. And Dr. Kaiser actually and Dr. Tech have both compiled, I guess is the right word, nice equation sheets that give you the things you might need in order to solve problems. So that's the other question that I didn't get asked. I didn't mention, but that's a good one too. All right, if you looked in Canvas, and I'm going to go to a different screen here. We'll go to the modules page. I did make one change to the schedule with regard to labs. I'm merely swapping next week's lab for this week and vice versa. So we did free fall last week. And of course, Dr. Tech evidently told the section that he covered for me that it was due Thursday. And so it's due Thursday tomorrow for everybody. And It said 17th, and I don't remember what time I had it due tomorrow, but since Dr. Tech said Thursday, that's what it'll be. If you look at this week's lab, then we're doing inclined plane. The schedule said projectile motion. Of course, we'll do that next week. It was arbitrary which one was going to go this one, which one was going to go this week, which one was going to go next week. The reality is the inclined plane handout was ready to go. The movie was ready to go, and you'll see Dr. Tech in the movie. It's his movie, and so that's why we're going to go with inclined plane this week, and we'll do projectile motion next week. And I think that might actually be more timely because, as I think I told you, you got to expect some kind of a projectile motion problem, and doing that calculation on Wednesday and Thursday before the exam on Friday. Any one of your lab instructors, if it's me or Dr. Kem, we can help you in lab with doing the projectile motion problem next week. And if I'm going to give you one hint, I pretty much guarantee you that's a problem on the exam. Okay, much like the worksheet problem that I'm grading right now. Which is probably the next point administratively. I'm obviously behind because I was out of town for the family funeral on my grading. And remember, my rule was if you get the work in before I'm done grading that set for everybody, I'm not going to notice if Canvas makes it pink or something like that and says it's late. Okay, mastering's a whole nother kettle of fish. Mastering's just automated. If you're not in on time, it starts taking points off. So this is kind of your last call. I'm going to be getting grading done for worksheets from last week and the stuff that was due on Monday of this week. Obviously, the stuff you're turning in today, I'll get to maybe tomorrow. But if you're late and you've got a couple of worksheets that you're holding on to that you didn't finish from last week, now's the time to upload them because I haven't finished grading those sets, and you'll get full credit if you just get it in. And a couple of you are letting that slide a little bit, and that's not going to help you in the long run. One other thing regarding office hours and then electronic office hours via email. I think because there is a homework set today and we're getting closer to the exam, I am going to do office hours right after this class at 9:30, and then I'm not going to close Zoom up because I know a number of you go off to a 9:30 class and then you have questions to ask at 10:30. So I'll keep it open all the way through basically 11 o'clock, and I'll be sitting here working. I have 11:30 class, but I want to make both hours available this morning, and I may do the same thing on Friday as well, even though I don't normally have scheduled office hours on Friday. Next point, if you just have a question that you want to send me by email, that's great. I do this because I like it, not because I need the money or that I need the job or I need the prestige or any of those sorts of intangibles. I actually like teaching people things, and sometimes one-on-one is the best way. But like office hours is one of my favorite things to do. It's just it's sometimes hard to figure out the times to meet with people. But if you do have a question that you're asking, how do you do this? I can't get this problem right. You want to learn to communicate exactly what your issue is. I've had some people take a screenshot of the problem that they can't do, and that's great. The next thing I tell you is you probably ought to think about a screenshot of what you have done so I can figure out exactly how to correct you and help you. It's obvious in most cases you're frustrated because you can't get mastering to tell you that it's the right answer, right? Okay, I got that. I know you're not getting the right answer. You know you're not getting the right answer. The bigger question in physics, because it's a process, not an answer, is why. And the only way I can get directly to the why, what mistake is it that you're making? It's usually a little thing, okay? You forgot to do this, you forgot to do that, is if you show me your work. So merely telling me you can't get an answer right and not giving me any details about what the question is or what you've done up to date and why it's not working out for you, it just makes it hard for me to help you. And that is the job. It's not for me to redo your problem for you. It's for me to make you able to do your problem. And it's the difference between buying you a meal, buying you a fish, or teaching you to fish, right? One feeds you just immediately, takes care of an immediate need. One helps you long term throughout the course of this particular physics class and any other science class you're going to take. All right, I've talked for longer than I should. Any questions on any of that? All right, so everybody knows what lab is, everybody knows when the exam is, has some idea what the format is, how to prepare. If you got questions, you want to send me an email because it's an odd time and it's outside office hours, more than happy to entertain that. You got to help me out a little bit with what you've done though. All right, so we're going to do what we often do. We're going to talk about arguably two of the most important topics in In all of a physics 101 class, if you tell somebody that you've taken an introductory physics class, they're going to go, oh, then you've studied Newton's laws. And that's a reasonable expectation. And I want to back up real quick because I do want to make a point. You should be seeing my PowerPoint screen. And of course, this was on the video. Newton's first law: in the absence of any forces, objects move at constant velocity, and a special case of constant velocity is at rest. So an object in motion stays in motion, an object in rest stays in rest unless acted on by an outside force. First law of inertia, great, okay? We're going to spend a bit of time. There is a whole study of engineering called statics that deals exactly with that law, and it's broken out by itself. And that one's fairly straightforward. If there's no net force, there is no acceleration, and therefore the velocity is constant. And as a special case of constant velocity, rest. Zero is a constant velocity. All right, move on to the second law. And the second law says, well, okay, you find the net force and they don't add to zero. What happens? Well, the answer is the object accelerates. If the net force on an object isn't zero, it accelerates. And that acceleration will be greater if the mass is less, and that acceleration will be less for a given force if that mass is greater. Okay, so we say that the acceleration is directly proportional to the net force which is applied if they don't add up to zero, okay, in which case first law applies, and inversely proportional to the mass. And some of you, because this has always been an issue for me, maybe scratching your head saying, so isn't the first law merely a special case of the second law? And that argument has been made many times. I've made it. I don't disagree, okay? The second law encompasses the first law in the sense that if the sum of all those forces added up is zero, well, that means the acceleration is zero, and that means you got a constant velocity, zero being a special case. So the two laws are not independent in the sense that you'll see on Friday. The third law is a completely different kettle of fish, okay? Now, some things about this, and there's some, we did a vector addition on during the last class on Monday, adding three vectors because that sum of forces, every one of them has a vector symbol. They all have directions. One might be in the X direction, the Y direction. Obviously, a prerequisite skill to do Newton's second law problems is to be able to add vectors. And so as a prerequisite skill to adding vectors, you got to be able to get components of vectors, okay? And that's the deal. And you got to be able to see what vectors you're getting components about. And so even before that, we have a prerequisite skill of drawing these diagrams, which we call free body diagrams. And that's what we're going to talk about here in just a moment as I move on to the next slide. All right, so here's the first poll, I guess, which I'll launch. And this one you're going to see again, because the worksheet problems you'll be doing today, this is one of the free body diagrams. And so hopefully what you see, where does the poll go? Right in the middle of my screen. Of course it puts it there. You see an elevator. It's being lifted by a cable. It's moving upward, so the velocity is upward, and it's slowing. And then I want to know which is the correct free body diagram.
We're getting shown a different question.
Yeah, you're right. Thank you. It's because it advanced itself. Let me end this one, and we'll go back to the right question. Maybe I clicked the wrong button. Nope, that's the wrong one too. Stop. Appreciate that. Let me get to the right one. It should be 421. There it is. Launch poll. It would have worked because it was 5 choices, but let's make it match because there we go. Thank you. All right. Majority of people see it. That's good. And obviously these vectors aren't labeled. And so in your mind, you got to be going, okay, that vector is this force, that vector is this force. And we'll talk about that once everybody's in. About 10 more people need to consider it and vote here. And the majority have it. 24th, waiting on 3 more people because I guess we only got 27 today. Last one, maybe internet troubles. There we go. Everybody's in. All right. And so I'll share the results with you. And the majority view here, of course, was C. And I think I agree with C. And I think just kind of look at A. What vectors are these? That's maybe the first question for you. And so I think that's probably that tension in the cable that's referred to. And hopefully you recognize that's probably the weight of the elevator. And in this case, the drawing shows that the tension in A is greater than the weight. And that would give you a net force upwards. Okay, so that force net, I'm just going to write N for now, write out the word net. The net force is upward. Newton's second law says the acceleration is upward. And so that would be perhaps an elevator moving upward and getting faster, right? This one right here, well, now the tension looks about the same as the weight. This would be one where the acceleration is 0 because it looks like there's no net force. If I added these two, I'd make the tension a positive number and the weight a negative number. I'd add them up. They look about the same. They'd be 0. Acceleration is 0. Velocity in this case would be a constant. That's Newton's first law. The one that seems to fit the bill then is this one. And this one, the weight is bigger than the tension. If the weight is bigger than the tension, the net force is downward, okay? And so the acceleration is also downward. And that's what would be happening if an object was moving upwards, like this elevator, and it was slowing down, okay? Slowing down so that if you're looking at the motion diagram, we'd be looking at something like this. Okay, as in eventually it comes to a rest where I'm going time 1, maybe that's 2 seconds, 3 seconds, you get the point. This is where we start. Maybe it goes up 10 meters, something like that. Okay, and so that would be my motion diagram, and that's the picture that should be linked together in your mind. Those of you who pick D, I'm kind of at a loss for what the two forces in the upward direction are. And okay, force net be equal to 0 for E there, it's the same as B. And so I think that those two are redundant. And so they don't fit the bill. All right, any questions on that? It's an important one. I spend a little bit more time on it because that's going to be one of the problems that you all do when we break out into breakout groups later on. All right, stop sharing this. Let's go on to the next one. Hopefully I can hit the right button this time. There we go. And we'll move to the, oh, and by the way, if you want, there's proof that C is the right answer because somebody told me so. All right, not going to do this one today as a problem, but it's a perfectly legitimate problem to do. We'll probably see it sometime next week. Okay, the ball's hanging from the ceiling, and which of these is the free body diagram? As soon as you take your hand away, pull it off to the side, let your hand come away.
I'm not seeing the pole.
I'm sorry, what was that?
I'm not seeing the pole.
You're not seeing which? The pole?
Yes.
Okay, let me stop the poll then. And let me redo the poll. All right, and go to the right problem. Just hopefully that one, yeah. And then we'll relaunch it. You see it now?
Yes, thank you.
Okay, yeah, that was a Zoom glitch there. That one I'm not owning. I made the mistake the first time of hitting the wrong button. Zoom ended it on us.
You can see the answer.
Now the
Yeah,
answer.
now you can see the answer. That advanced. All right, well, that takes the fun out of it. All right, well, you see the answer, and a lot of you are getting it. Hopefully you can see why, though, okay? So we'll end that. Good on the 17 of you that can read. You passed. Good work. Let's see. I'll draw my free body diagram right on top of a technique I don't recommend, but hopefully you recognize that's the weight. And since there's a string attached, that's the tension. Okay, and so there's a two. You'll sometimes see people write weight as F sub G, force of gravity. And I try to stay with the symbols in our book. Our book definitely uses W. You'll also see sometimes people will say tension F sub T. Okay, now the one thing I want, sometimes people jump on C. That's probably, if you do the net force here, I can see that there's a component of weight right here. I don't know, I might call that the Y component. If I think of a coordinate system where that's Y, which I'm going to tell you in a bit is sometimes a good strategy, and that's X. And we did that with inclined planes. We can tilt the coordinate system. The y component of the weight is pretty much balanced by the tension. And you can see there's a what would be an x component of weight right here. And that's not balanced by the tension. So in this particular problem, while it's an interesting one, the tension and the y component of weight, they seem to be balanced, and there's no motion along that direction. It's a first law problem. The sum of the forces in the y direction are going to be zero. Tension up, the y component of weight is downward. But this component of the weight, the x component of weight, isn't balanced, okay, isn't canceled out by the tension. It's left as the net force then, and that is what ultimately causes the acceleration, because I think you realize if you let this go, it would initially accelerate in that direction, tangent to that arc. And so that's what this would be. This might be the acceleration vector in the problem, but that's not what goes directly at the origin of a free body diagram, okay? All right, let's try to move on to the next one now without showing the answer. 423, launch pole, and then I'm going to go to there, and hopefully you're not seeing the answer this time. There's a rope here, right? Car's being towed. Constant speed. What's the correct free body diagram? And in your mind, you should be thinking, what are the forces here? All right, just looks like everybody's in, so we'll end it. Good. And again, the majority of you are getting the right answer. And I'll even talk to C. C looks close, right? Because let's label these forces. That's the normal force. Of course, that's the weight. Always have it. Okay, we don't deal with weightless objects in this course. That's the tension, right? There's the force of the tension. And so what's this gonna? What's that gonna be? Well, I guess that's got to be friction or maybe drag. Those are the two forces that would be in that direction, would be opposing the motion in the car. And so what's the difference? So I'm going to call it, let's call it drag. Why not? Or friction, your choice, because either one could be right. And I think I said we lump them together at times. So why is C not correct? In your free body diagrams, you should make some effort, like it's being done professionally here, obviously, to kind of show the size. This guy right here looks to be about the same as that guy right there. Okay, so they're balancing each other. The car isn't moving in the y direction, but we also said it's moving in the x direction at a constant speed, in which case that tension and that friction drag force back there also have to be the same size, because that would be zero net force and would be zero acceleration. Zero acceleration means constant speed. And that's why D is the best answer. C is a good answer in the sense that it has that fourth vector, okay? It just isn't quite long enough, so it's not the best answer. You can see this car, you would have a net force in the x direction. There's my net force. And so I would have an acceleration in the x direction, and then you wouldn't be answering the question because you would not be moving at a constant speed in that case. Of course, same way E is wrong in the sense that it's too big a drag. That would be a car slowing down, right? And B also would be a choice. That would be accelerating, unbounded, no friction, no drag, slowing it down. That guy would be going really fast, real quick. And then I'm not sure how with choice A, nobody picked it. So that's a good thing because the car wouldn't be moving at all in the X direction. And that's not what happened here. All right, everybody good with that? All right, let's go. I think this should be my last one. So let's get the poll working first. Okay, and then let's go on. There's my answer for the last one. And here now your car is on a hill and it's parked. That's kind of a key word, right? It's parked. All right, somebody sees it, so we got it. Park means V is equal to 0. Ever had a car parked on a hill and you don't put the parking brake on and it starts rolling a little bit? Scary thing. Only happened to me like once. It was an old car. '21, '22. You guys are doing good. The majority have it, I'll tell you that. All right, everybody's in. The majority wins, as is often the case, but not always. I'm going to draw a bad free body diagram here. I'm going to do a bad technique. Always have weight, right? So we're good to go there. Let's see. Normal force, actually that way. Okay. Normal to the surface, right? There's my surface. The normal force is always perpendicular. That's where it gets the name. It's perpendicular to the surface. And now with this, there would be a component of weight that would allow the car to go down the hill. There's also a component of weight. Again, we've rotated that coordinate axis like we like to do. Make that the Y direction, make that the X direction. Handy coordinate system. But it's not rolling down the hill due to that component of weight. So there must be some sort of force right there pushing back. I'd argue it's probably friction, okay, right here at the wheel. We've locked the wheel in place with the brake, and then there's a friction force actually at each of the four wheels pushing that way. And when we draw the free body diagram, we take all of those guys and we put them right to the center of the object right there. And so I think C is the best answer for that. D, and don't like that, right? We don't like that because that would cause the car to roll down the hill. And I think that's a problem. So would A. A would allow the car to roll down the hill, wouldn't it? And B absolutely would have the car rolling down the hill. So that's a problem right there. Hopefully you see those. We'll talk more about this problem. I guarantee you'll see this one next week. You may even see it here just in a little while when I do a problem. Any questions on any of this? All right. Share the results, which I don't think I did. The majority did get that one right. And we'll put this away for now. I'm going to stop sharing that with you. And I'm going to go over to do some worksheet problems here. And I'm going to do two. And then you're going to we'll go into groups and we'll break up. You actually have four, but two of them I think you'll find are pretty trivial, I hope. I hope you see it that way. All right, so what I'm going to do is start sharing my iPad, and it takes me a second to set up AirPlay here. Screen mirroring. Come on, yeah, found my, there we go. All right, and hopefully you're seeing the worksheet for today in my app Notability, and I give you some hints, okay? And I'll be honest with you, I stole these from somebody. I didn't write them all. I think they're good. Some of you may find them a little bit constraining. You know, you're doing rote and you're not getting any value out of it, but I would recommend them if you don't have any firm objection to them. Do them this way. First, on the free body diagram, I said I exhibited bad technique because I was drawing forces right on the car or right on the ball. We want what your choices for the answers were. We want you to draw a dot and draw the forces coming out of that dot. And that dot represents whatever the object is, okay? So bring your free body diagram away from your physical diagram, which has the picture of whatever it is, so it doesn't clutter things up. Include angles wherever you can, okay? If there's an angle necessary, put it on your free body diagram. A lot of people like to push with forces, not recommended, okay? On my car, I might show something pushing, but we want to think about just make all your forces pull on the dot, which is the thing that represents our object. Make the forces darker. You'll see what I sometimes will do is I'll draw my axes dashed and I'll make my forces solid. If you like two colors, go that way. Not necessary, but that's something to do. Initially here, your forces will be weight. Almost always. I can't think of a case we won't have weight. We're going to deal with friction, tensions in either strings or springs, and I suppose a spring could compress and it would push technically, but when you draw your free body diagram, have it pull on the center, okay? And normal forces that are anytime two things are in contact, that is a normal force. We'll add drag and thrust later on. Make sure you establish a coordinate system. Okay, it's always suitable, and I showed two examples where you can rotate your coordinate system. If the thing is primarily vertical, okay, make sure that you put the y-axis right on the axis where the forces are. You want to minimize the number of forces you got to find components of if that's necessary. Okay, we're going to talk about how to calculate weight next week, and you're going to, if you've studied physics, you know that that equation is going to look a whole lot like Newton's second law. And I think that fact confuses a lot of people. Don't confuse weight with the result of Newton's law, which is mass times acceleration. Our job is to just put weight in with all the other forces we have in our catalog, add them up, find the net force, and then set that equal to mass times acceleration to determine generally the acceleration, and then the velocity, and then maybe even the position as far as you can take your problem. Remember that all forces are vectors, and any vector in the same direction must have the same sign. That's acceleration and forces. Any two vectors in opposite directions have to have opposite signs when you add them up. Okay, and so I think it's time for me to just do a problem here for you. And this problem is supposed to demonstrate a point that what we've been doing for the first 3 weeks in physics is absolutely related to what we're now doing with Newton's laws. Okay, we didn't spend 3 weeks on motion, velocities, accelerations, positions to be completely separate from Newton's laws. In fact, you've got a baseball pitcher here. That's my little sketch of a stickman baseball pitcher up on the mound. And you're seeing the ball is currently in position 1, hand back behind his head, and he's just going to push it forward. Lousy technique, I know, but it's a good physics problem. And as he throws the ball, from the time he starts with it at rest behind his head till he pushes it in front of his head, that distance is about 1 meter, okay? And we know that when it leaves his hand, the ball is going with a final velocity of, what do I say there, 46 meters per second. Okay, so that's final. And the velocity initial, well, kind of implies it is 0, right? And that takes place over a displacement of 1 meter. Everybody good with that? Put my units on there. Okay, you know, I don't need a unit on the 0, but if some of you want, go right ahead. We're told the mass of the ball, so I'll put that in right away as well. And let's see, the mass of the ball is given in grams. Remember, there's 1,000 grams in a kilogram. So I can almost do that one in my head. 145 grams is 0.145 kilograms. That's often the reason people get a problem wrong. That conversion right there, similar to the one between centimeters and meters, is a big one as well. All right, so I think that's all I'm given in this problem.
Dr. Jablowski?
Yep.
Isn't your velocity final supposed to be 46 meters per second?
What did I write?
Just meters.
Oh, who said that? You want that?
Katie Ekoff.
Katie, I owe you a point. Good catch. Katie gets an extra point. Yeah, I do something like that because I'm talking and I don't write the right thing. Okay. I hope I said meters per second, but I certainly didn't write it. So there you go. Everybody good now? Katie +1. All right. So now what do we need to get out of this? Well, let's draw a free body diagram. I'll take that ball. There it is. Okay. And it's actually a pretty easy free body diagram. The pitcher is applying a force. Okay. It's applied, we sometimes say. If you think about which force in our catalog, it's probably a normal force. You know, the surface of your fingers touch the ball and push it forward. If you don't like a pitcher, think of a shot putter in the palm of the shot putter's hand, because that's really what we're modeling this problem as. You know, a real baseball pitcher snaps wrists, snaps arms, elbows, all those sorts of things to generate extra speed and extra force. Okay, we're not considering that. We're making this model very simple and probably unrealistic, but you'll see the answer. Okay, so that's my free body diagram. There's probably a drag, which we're going to ignore. Okay, but in order to get that force, it seems we have to find the acceleration, right? And so how am I going to get the acceleration? Well, we said that the final velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. And I went with that equation because I realized the problem gave me displacement. Had it given me time, I might have gone with a different equation, right? I might have gone x final is equal to x initial plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. But I don't have time here, I got position. So that was the equation that experience has taught me to go to. If you don't see that right away, write down all your constant acceleration equations and see which one works. Well, hopefully I know everything in that equation, and I think I do. It looks to me like I know the final velocity. Hey, I know the initial velocity. I can just make that 0. And I know what the displacement is. So I think the acceleration is just the final velocity squared over 2 times the displacement. And I did the algebra hopefully in one step. If it takes you 2 or 3 steps to do it, that's fine. You know, if you're not comfortable with algebra, I divided by 2, I divided through by delta x, and I did it all at once. And so now I could go in and I can put in my initial velocity, 46 meters per second. And that, of course, is squared. Don't forget to square it. And then divide by 2 times the displacement, 1 meter. And I want to get this right here with units. I took 46 squared and I divided it by 2, and I got 1,058, and I had a meter squared per second squared divided by a meter. Well, that's a meter per second squared, so that worked. Okay, and if you notice, there really were kind of 3 math steps I did to get that. First, I did the algebra to solve for the acceleration. Then I plugged in the values that I knew, and then I took the numeric values and I got the 1058, and then I took the units and made sure that, sure enough, that's a lousy looking second squared there. That guy right there is a second squared. And so, you know, I'm confident in the answer because I kind of went through it 3 times. All right. And if it's a little math mistake there or something, you plug the wrong numbers into your calculator, we could probably live with that. But we can't live with you know, conceptual errors, and that's the thing to make sure you're not doing. All right. So now that I got the acceleration, because you know, it's a problem we've been doing throughout the first 3 weeks of the course, what does Mr. Newton have to say? Well, he says that force which is applied will be equal to the mass times that acceleration, right? Which is equal to the 0.145 kilograms times the 1058 meters per second squared. And when I went to my calculator, I found that that gave me 153 for the numeric value of 1058 times 0.145. And hopefully you saw in the video that a kilogram times a meter per second squared is indeed a Newton. Okay, and so that's that tells me how much force the pitcher must have applied to the baseball in order to cause an acceleration, which would, after 1 meter of displacement, give a velocity of 46 meters per second. By the way, that's about 100, what I say, 102, 103 miles per hour. That's a pretty good fastball, and apparently is the highest velocity pitch ever recorded with a radar gun. All right, and so the last thing it says is, well, what does that number mean comparatively to other forces we see? And so let's compare it to, say, the weight of the pitcher. And I assume the pitcher nominally 180 pounds. That's a good weight for a high-level athlete. And so the question on weight, I had to convert that into newtons in order to do a comparison. And it's just a little practice on unit conversion here. Okay, a pound. And then I know that there are 4.45 newtons in every pound. And I had to go to the back of our textbook. I think it's the back. It's either the back or the front. There's a conversion factor. I certainly didn't have that one memorized. But when I did it, I found about 800 newtons was the weight of an 180-pound person. And so that looked good. And then the last thing I did is, well, I took the ratio of these two because it says compare. And so I said, well, let's look at 153 newtons divided by 800 newtons just to see. And that's about 0.19. So the pitcher is putting almost 20% of his or her weight into pitching that, into the force that they're putting on that ball. And I suspect better technique will mean you won't have to put as much of a fraction of your weight into it, but you know, it's quite a bit. And so that's how you're able to get a fastball moving pretty quick. Any questions on that problem? it's designed, and it's to make a point mostly that, there is a relationship between that acceleration in Newton's law and the force which causes it, and the motion that must necessarily result because of the acceleration. They're one big package. They're not something that we can separate out. All right, I'm going to move on to the last problem I'm going to do. You're going to do some elevator problems like that first polling problem. And I'm going to go on to this one right here. And if you can see in number 8 here, you've got a weight. You've got a weight of 174 newtons, and you've got an object on an inclined plane. It's just a block. And so let's see, let's draw those forces. And not, this isn't a free body diagram, but me sketching out forces. Okay. Weight, that's the 147 newtons. The normal force, and this is why it's right there at the surface, right? And it's perpendicular. And then of course we've got this applied force right here. It doesn't say how. Maybe it's a rope that we attach to the thing. It's applied, so maybe it's a tension. I don't know. Maybe it's somebody's pushing on the backside, but there is an applied force, and if somebody pushes, it would be a normal force. We can see those are the forces we can identify. Anybody think of any others? Yeah, me neither. And so here's what I kind of propose for you. Let's think about a coordinate axis like that. Okay. Why? Well, if you look, what I'm calling the x direction here, that's the same direction as the applied force. The normal force then would be in the y direction, and my weight, well, it would not be in the y direction. So here's what I'm thinking. Let's draw a coordinate system, kind of dashed. X and y. And let's see, the force applied, let's go to a different color. I can do that. If you don't on your paper, that's fine. There's the applied force. Maybe it's a tension. I'll just go with A. Let's see, the normal force would be right there. And then where would the weight be? Well, let's see, the weight would be right there in this diagram. So I don't know, maybe at an angle like right there. Okay, and so that's my weight. And I said on your free body diagrams, do try to draw in the angles. Okay, if this is a 24-degree angle, well, that's a 24-degree angle. And in a piece of very practical advice I got in graduate school, of all places, well, we didn't solve a lot of problems like this, but this allows you to look in 24. Let's get rid of that and make it bigger for you. Put it out here. Is don't draw angles that look like 45-degree angles. Okay, a 24-degree angle is much smaller than a 45-degree angle. Is it reasonable to look at your sketch if it's and think that's the 24-degree angle or the one that I labeled a 24-degree angle? I can go through a rigorous 10th grade geometry proof to prove that alternate interior angles and corresponding angles and all that rigmarole to prove that's the 24-degree angle, but it just looks like it's the 24-degree angle. It's not the other one, the 90 minus 24, which is much bigger, which would be, I guess, right there. Why is that? Oh, because I've still got the eraser tool on. Okay, it's the angle that I've shown. All right, well, let's move on. Got to do some math here.
I have a question.
Sure, go ahead.
Do we have to include like friction?
In this particular problem, does it say not to? You could, except I'm not giving you enough tools to deal with friction.
Okay.
I could make the problem harder and include it. And in this case, when I wrote the problem, do I say it ever? So we'll say this is a frictionless incline. And we will definitely do this problem again with friction because it does change the answer. So let me insert a word there. But if there is ever a doubt, this is a frictionless incline. Ever a doubt, ask. Okay. Yeah, I would need to give you another piece of information that there's something called a coefficient of friction we'll talk about, not addressed in this problem. And so that you can assume, we'll assume there is none. We'll also say words like smooth, that means no friction, okay, as opposed to rough, which means there is friction. Look for words like that, but that's not ever going to be something you're tested on. So if that's ever in doubt, should I be considering friction? Should I be considering drag? That's absolutely a fair game question to ask about any question that's asked of you. Okay, good question. Let's give myself a little more room to work here. Okay, and I think the point of my coordinate system, the way I drew it, is let's see, the applied force is only in the x direction, right? And the normal force is only in the y direction. So what I have to do is I got to get the components of the weight, don't I? And so it looks to me like the x component, let's see, the x component would be, let's go to a third color here. The x component would be right there or right there, opposite the 24-degree angle. I draw it in either place, but if I draw it at the over where it makes a right triangle, it's pretty clear it's the opposite side of that 24-degree angle. So it would just be the weight, which is 147 newtons, times the sine of the 24-degree angle. Make sure your calculator's in degrees. And what I got when I did that was 59.8 newtons. Okay. And then once you got one sine picked, whether sine or cosine, you look at the other and the adjacent side, which I guess would be right there, wouldn't it? That's the y component. There's the x component. Okay. Be times the cosine of 24 degrees. And that's going to be 131 newtons. Okay. And so you might go, well, let's see, aren't they both negative? They're both, you know, the weight here is in the third quadrant, so they are negative. I'm not going to make it negative for two reasons, but I think that's a good thought. Hold it, keep it in your head, because it's going to be handy next. If this block is at rest, then the force in the x direction, that's the net force in the x direction, has to be 0, and the force in the y direction has to be equal to 0. Well, in the x direction, I got the applied force, and then I'm going to add on the weight force, and it's got to be 0. So that's the applied force plus a minus 59.8 newtons. So if that's good, those two are going to add to 0, the applied force pretty clearly has to be 59.8 newtons. I probably should round that. Well, I got 3 digits there, 2 digits. I should probably call that 60 newtons, right? And I probably should have done some rounding on the picture problem too. Okay, so in any event, next one is in the y direction now. Just look at it. I've got the normal force plus the y component of the weight, and that has to be equal to 0. So the normal force plus a minus 131 newtons also has to be equal to 0, and that tells me right away that the normal force is about 130 newtons. I round it all in one step there. Okay, and so it's a big deal here that you pay attention to what I said. Notice the applied force was to the right, it was positive. The weight component was to the left, and it was negative. Notice that the normal force is upward and it's positive, and the y component of weight is downward, and so it's negative. And it follows my rule that two vectors in opposite directions must be negative, and hopefully makes the problem pretty easy to solve. Now, these are both vectors, so I probably should say something like this is 60 newtons to the right, that's 130 newtons up, just to be complete on my answer, but that's what I got. All right, now here's what I've done. You've got 4 more problems. We're going to be talking about Newton's third law on Friday. We'll come back. I was hoping we get to at least start these problems today. We're going to work these problems then on Friday in breakout groups. I'll have some polling to do on Newton's third law, and then I don't think I have any examples. We'll just jump right into you working in groups on the 4 problems.
I have a question.
What's that? Go ahead.
If we're working on these on Friday, does that mean these are not going to be due?
They're not going to be due. Yeah, I didn't give you enough time. So they'll ultimately be due on Monday then. And I do reserve the right to add a Newton's third law problem if I can come up with a good one. But we'll be working on these 4 problems that are in the worksheet groups on Friday. All right? Yeah. Last chance. I'll be hanging around for any questions people have on homework. I know there were a couple. I think I answered one last night. I'm not sure I answered any of the others, But let me go refill my coffee cup. Everybody else, have a great day. Hopefully, Dr. Kem will see some of you in lab today. You'll be analyzing a video, and hopefully you saw it there on my Canvas screen. And I'll see the 2 lab groups that I work with tomorrow at the normal lab start times. And we'll start up with a quick meeting, and then we'll move on to go do the work. And I will make this week's lab due next Thursday as well, because you do have, I can't just make you do the lab in one day. All right, any questions? 9:20, so I got to let you go on to your next class, and I'll be here. I'll be back in a moment just after I fill up my coffee cup. And
I have a quick question.
Sure, go ahead. We're now in office hours before I go, but let me stop sharing this. Go ahead.
You haven't posted any of the recordings. I wasn't able to log on Monday, and I wanted to know if you were posting them.
Yeah, I'm behind on that. Okay, so I think the question is, did I hit the button on Monday? If I did, it'll be up in the next day or two.
Fridays isn't on there either.
I don't know if, did I, I'm not sure I recorded on Friday. I was doing that.
I think you did. I was there Friday. I just wanted to.
Okay. I will catch up on those things. I got up, I think I did them last week sometime. I caught up then, and I'm not going to do them every day. The bigger video to watch as well, though, is the pre-lecture video. I always do an example problem in that thing too, or generally do an example problem, but I'll get those things posted.
Okay, thank you. I just wanted to let you know.
Oh, no problem. Yeah, believe me, grading and catching up on admin like that after being gone out of town for the 4 days, I'm certainly behind, and we'll be catching up here.
All right, thank you.
You bet. Other questions?
I have a quick question real quick.
Okay, we'll give it a shot.
The extra practice problem sets, are those due for credit or?
No. Those are just, if you're comfortable with the worksheets you've done and the regular homework you've done and all the polling questions we've done, and you're happy with your preparation with that, which truthfully is enough. It's a lot of work. Nobody's denying that. But if you've done all that and you still think you aren't quite solid on some area, completely voluntary to do the extra. They're working.
Okay.
They don't factor into your grade other than the effect that they have on your performance on the exam.
Okay.
Fair enough?
Thank you.
Yeah.
My question was about the exam, actually. Is I've extended time, and I wasn't sure how that would play out.
Yeah. Okay. So I'm going to design the exam to be about an hour, maybe an hour and 15 minutes long. Okay. But you're going to have all day. I'm going to give you 24 hours to work on it.
Okay.
Okay. So there's no clock. There is that is technically possible to put a clock on the exam, but I'm not going to do that. And so if that's fair with you, so if I'm designing it for an hour and 15 and you take 3 hours, I'm not going to know or care, quite frankly. So as much time as you need within the window of being open. And I think I may have explained why I'm only going to go, you're not going to get 3 days to do the exam. I did that in the past, and that allows for, let's just say, usage of unauthorized sources. How's that?
Okay.
And I'll just leave it at that. But I was actually surprised that I had some students do that on my final exam last semester. And the answer is you just can't, you got to keep it to a reasonable time so that they can't spend too much time getting help in unauthorized areas. All right. Fair enough, though?
Yep.
All right.
Thank you.
You bet. And you catch up, man, because I'm behind on grading worksheets. Get those problems done and uploaded. Even if they're not 100% correct, you'll get the feedback from it. And so I recommend you've got a couple you're behind on. Now's the time to get them in because I'm behind on my grading.
All right.
All right. You bet.
Hello.
All right. What can I do for you? Question or? Hey, let me stop. Let me mute myself for just a second.
Hello?
Run into the kitchen and grab a cup of coffee. I'm dying here.
Okay. So I have a question on it's actually the last two worksheets. Sorry, my internet connection is okay.
All right, sorry about that. What can I do for you now? Still there? Nothing in chat.
Okay, sorry about that.
Okay.
Okay. I had a question on the last two worksheet 3.3, the circular motion worksheets.
Okay, 3.3. Getting there. Hang on. Which problem's troubling you?
Page 2, 1B.
Page 2, 1B. All right, gotcha. Okay.
Also 1A.
Okay. Let me close this thing. And this is worksheet 3.3, right? I do have that saved here somewhere, I think. There's 3.2, there's 3.3. Come on, open up. And don't do that. And I'm going to share my screen with you here. Come in here. Oh, stop it. Stop it. Screen mirroring. Zoom. All right. Put that away. Do I have the right problem?
Yes.
All right. So I guess the kind of drawing a picture here. There's my river, okay? And let's have the river current go that way, okay? And how big is the river current? 5 kilometers per hour? Okay. And it says the boat is traveling upstream at 25 kilometers per hour. There's a boat right there. These are the kind of sketches we draw in physics, okay? And I guess, I mean, they're pretty crude, but that gets, is that the picture that you had in your mind when you read this?
Yes.
Okay, so now somebody is watching this person from the shore here, okay? And I guess the equation that we would look for what this person would see, that's the speed of the boat with respect to the shore, is going to be equal to, and this is the rule we said, it's the speed of the boat with respect to the water, okay? I guess I'm using capital P, plus the speed of the water with respect to the shore. My pen just turned off. There we go, with respect to the shore. Okay, does that make sense?
Yes.
Okay, and the reason I know I wrote that is I can see that and that, they kind of just cancel. And so that tells me that the speed of the boat relative to the water, and that's what we're saying, that 25 kilometers per hour, is with respect to the water, right? That's what that means. So that's 25 kilometers per hour. And now the big question is, what am I going to do with this? You know, it's 5, but they're in opposite directions. So what do you think I'm going to do with that 5? Choices are add or subtract, right?
5.
Which do you think?
Yes. Subtract.
Yeah, it sort of makes sense that you're going to subtract that 5 meters per second. And so it looks to me like the answer is 20 meters per second, right?
Yes.
Okay, so that's the first one. Crude drawing.
So like the main one was.
What's that?
No, sorry.
You're good? Okay. So
Yes.
that hopefully makes sense there. And you know, I have a very formal equation, but if this is one that you almost in your mind go, does that make sense? You know, so in one hour, you'll move 25 kilometers if you were to move, if the river was long enough, but then the river would push you back 5, wouldn't it? And so your net would be 20 kilometers in that hour. And so hopefully that makes sense in that sense. All right, so now you got the this person on the boat. I'll make the boat a little bit bigger. And again, relative to the shore, we've got the boat moving at 20. I'm missing a K here, aren't I? In all of these. Yeah, they're kilometers per hour.
Okay.
Yeah, so I apologize for dropping that K there. And that's per, not second, it's per hour, right?
Hour.
This problem's per hour. Yeah, so often we use meters per second. I almost just by habit write meters per second for speeds. All right, but kilometers per hour. And now we've got a person in the boat. And that person, it says, is walking that way at 3 kilometers per hour. All right. And so it's going to be the same equation, just different terms. But it comes down to if the boat is moving 20 kilometers per hour relative to the shore, and the girl is moving at 3 kilometers per hour relative to the boat, do I add the 3 or subtract the 3 in this case?
You subtract, and that's you subtract the 3 because it's moving back?
Absolutely, yeah, because they're in opposite directions. The formal equation would be the velocity of the girl relative to the shore is equal to the velocity of the boat relative to the shore. And I'm putting that in the wrong order, so let me get it in the correct order. The velocity of the girl relative to the boat plus the velocity of the boat relative to the shore. And then again, the boats cancel. I'm left with girl shore. Okay. And so I would go minus 3 kilometers per hour plus 20 kilometers per hour. And that's 17 kilometers per hour. But what your intuition was, you subtract them because they're in opposite directions, and that would be exactly right. Okay. What else can I do for you? Does that make sense?
Okay.
Yeah, the formal.
Yes.
The formal equation is good, but then at the end you go, do I add it or I subtract it? What's positive and what's negative? And in every case here, I made that positive. Positive X to the right. Anything going to the left, I subtracted, didn't I?
Yes.
All right.
Okay. I also have a question. During when I was doing some of the homework problems, I don't know, I noticed that acceleration sometimes will be positive. Like, I have a question. Is acceleration, because I always assumed that acceleration will always be negative, but is that not true?
Which problem are we talking about here?
No, it's just like in general in the homework questions in the master in physics.
So you're saying, should you take the absolute value to get when you turn in an answer?
Yes, or like.
Yeah, here's what I think. And, you know, I'm the one that grades most of the time, and I'm pretty sure mastering adopts this. If we ever say something like, what is the magnitude of a particular thing? Well, the symbol we use for magnitude, like a vector, let's just say I've got a velocity vector, right? And that's a velocity vector. And when we say, what's the magnitude of it? The symbol we put is the absolute value sign. In which case I would say, yeah, you always turn it positive. When somebody asks you what the magnitude is, magnitudes are positive, and we're reminded of that by the symbol we use. Okay, so it's very consistent. If you're trying to evoke a direction, you need to show that it's to the left, for example, of whatever the answer is, or it's down. And the problem asks, then you would need that negative sign, right? And so it really depends on a particular problem, whether you include a negative sign or you don't, based on what you were asked to do in the problem. Does that help at all?
Yes.
Yeah, and if there's ever a question on that, you know, if you're doing mastering, I guess you could try positive, try negative, I suppose. Of course, that burns 2 choices. But if you're ever confused, that's a quick one. Say, you know, just shoot me an email saying, in problem whatever, and you can screenshot it if you want. Is it expecting a negative number or a positive number? And I'll read the problem and tell you what I think. Okay.
Okay. So,
Yeah.
but
And I read part of this is learning how to read problems and interpret what they're asking you to do. And that you've got a good question there.
When we're going down an incline, accelerating down an incline, do we? I guess this also goes back to what you were saying, but like, is it a positive acceleration?
Yeah, that's it depends is sort of the answer. I'm just going to can I go to just a plain screen here? Let me show you a couple examples. How do I get a new note here? And to get a new note. Let me, I mean, you see Notability. They put their advertisement for you. Select it. I want to select one. I just want to open up a blank one. How do I start? I'm so new with this app that I don't know. I may not waste your time here. We'll cancel that, and I'll just stop sharing that, and I'll just go to the whiteboard here. All right, so I'm going to draw two inclined planes. One is going to be that way, and then another one will be that way. Okay, and so let's put a block right here because that's what I just did, and let's put a block right here. All right, and normally, like I said, it makes sense to do something like this, right? Make my coordinate system rotated with the but most people would probably do that on this side, right? And so this thing right here, I expect an acceleration that way. I would call that a negative x, right? That acceleration would be in the negative x direction. Whereas this acceleration right here, both are down the inclined plane, right?
Yes.
This one right here on this coordinate system is a positive x, right? And so it really depends on how you draw your coordinate system, doesn't it? And I would argue that both could be right, but your work has to be consistent with whatever picture you draw. Now, I know, like on the example I did today in class, I made that force positive, right?
Yes.
Let me get rid of this and redraw that, I guess, now. And I made this force positive, but then the weight force, which was down here, I made its two components negative, didn't I? And that was consistent with this coordinate system. Had I drawn the picture of the inclined plane really by going around to the other side of the inclined plane and doing the same drawing, right? I could have come up with a completely different set of, I would have made that a negative, I would have made that positive, and the weight I would have made positive and negative, right? And as long as I was consistent with my picture and the work I did, then both could be right. The only thing that we require in a physics course is that your work be consistent. But one of the hard parts for me when I'm grading it is some of you can make something positive, some of you could make something negative. As long as you're consistent, you have to accept both. Yeah, and my rubric has to anticipate that you might see the problem a different way. You might see it from the other angle, and I have to be able to accept that. That's why you'll see I often draw the picture that I want. So then most people follow my picture and use the convention of right positive and up positive, and that makes it a little easier for me to grade. But if I ever just leave you to draw a picture, I've got to be willing to accept whatever convention you pick. Yeah. All right, probably more than you wanted to hear, but that makes the idea.
Yeah. Yes, it did. Thank you.
All right, any other things?
No, as of right now, no, I do not.
All right, I'll be around. I'm going to mute myself and do some work here. I got some grading to catch up on, but I'll be around. I know there'll be some people probably coming back after the 9:30 class at 10:30. So if you need anything else here this morning, I'll be here.
Okay. Thank you.
You bet. Take care. Mute.